Hello, everyone. It's really a great pleasure to be here today and in such distinguished company. So we're going to hear from the most recent Canada cifar.ca chairs who work in reinforcement learning. It's the field where I spend most of my time, so I'm very excited to hear what they have to say. And so what we're going to do, first of all, is I'll ask everybody to introduce themselves and tell us a little bit about their research in reinforcement learning and just more broadly. And we'll start with Csaba and go all the way.
All right. So I already did my introduction yesterday, so I don't know. Probably people remember that I work in reinforcement learning and theory, and I'm very happy to be here, and I'd be curious about what questions you guys are going to have.
Hello, everyone. So I'm Yaoliang Yu. I'm from University of Waterloo and the Vector Institute. My main area of research is in machine optimization for machine learning, where we look at different first-order grading algorithms. How do we efficiently implement them when we have some structure in the problem, and how do we provide the theoretic guarantees when we deploy the algorithm in a distributed environment. Another interest that I built in the past few years is about deep generative models, where I'm fascinated by the interplay between many ideas from a number of fields. For instance, we have probabilistic inference, we have deep learning, we have statistics, probability, and optimal transport, all of these great ideas that you can find in deep generative models. So I'm very happy to be here, and thank you.
Hi, I'm Sheila McIlraith. I'm a professor in the computer science department at the University of Toronto, and I'm also a member of the Vector Institute. My research has historically looked at deliberative reasoning tasks, what you can think of as thinking tasks, I guess, and largely at sequential decision-making tasks. More recently, I've been focusing more on reinforcement learning and really trying to understand where symbolic and sub-symbolic reasoning can come together, re-looking at some of the problems that we've looked at historically through the lens of logic and probability and models, but now looking at it anew through the lens of perception and deep learning, but bringing to bear, I think, a lot of the interesting ideas from symbolic reasoning.
I'm Nicolas. I'm a researcher at Google Brain. I'm also an adjunct at Mila. Most of my work is in optimization, but I guess there were already 7 chairs in the foundations of core ML, so I ended up in the reinforcement learning panel. I think similar to what Courtney said, at some point the optimization for the sake of optimization started to bore me a little bit. And so now I'm moving toward understanding reinforcement learning from the perspective of optimization. Like when we talk about exploration in reinforcement learning, what does that mean from an optimization perspective? I think fundamentally what interests me is how can we learn with fewer samples? There are many directions to approach this problem. Meta learning is one of them, transfer learning. But one of the ideas that I worked on and I want to pursue is this idea that when you see a sample, how much information can you extract from that sample? And right now we're extremely wasteful. We basically compute a small gradient, move, and then we throw that sample away. And I believe that there's much more information we can gather from it, and how to do this efficiently is part of my research.
My name is Jakob Foerster, and I'm currently at Facebook AI Research in California. I'll be starting at Toronto, at the Vector Institute in the fall of 2020. And I've been really driven by the question, how can we do machine learning in a world that contains other learning agents? So obviously when we do reinforcement learning, we typically assume that the environment is static. So the agent can interact with this environment over and over and over again to learn an optimal policy. But clearly the moment we deploy anything in the real world contains other learning agents. Those could be the human users, those could be other learning agents that coexist in the same environment. Think, for example, about self-driving cars. And the presence of other learning agents fundamentally changes the kind of problem we're facing. So this, for example, is a vast multi-agent problem. We're all here, we're communicating, we're thinking about the intents and points of views of others, and we're trying to coordinate and collaborate. And I'm thinking about how we can bring those capabilities that are so key for allowing agents to cooperate in large numbers to machine learning algorithms. And I've studied this using deep multi-agent reinforcement learning, where I both develop new benchmarks, but also think about new learning algorithms. And I'm really excited to pursue that agenda at Toronto.
Hello, hi. So my name is Pierre-Luc Bacon. I'm a new assistant professor at University of Montreal, affiliated with Mila. I've been working for the past few years on the problem of temporal abstraction in reinforcement learning. Actually, I've been working with Doina here, who was my advisor during my PhD. Generally speaking, I'd say I'm interested about the grand challenge in machine learning, which is that of learning over a long horizon. So that goes back to the question of credit assignment at the really high level. And I'm interested to tackle that question from, I'd say, a representation learning point of view first, but I'm also very interested in looking at formulations of that problem that are rooted into optimization methods. And in particular, I'm interested at the interface of optimization and automatic differentiation methods, which are so important for us in our field in deep learning. So these are the things I was working on, and that's what I keep doing right now. And especially these days, I'm interested about bi-level and hierarchical optimization formulations, which are really useful when it comes to talking about meta-learning. So that's where I'm hoping to go over the next couple years.
Thank you very much. So I have a question for the people who are new to the Canadian academic system, so new recruits. That includes you, Csaba. Why Canada, or why did you choose to join academic institutions in Canada?
We should go the other way around.
Anybody can start, like, I'm looking for volunteers.
But new recruits, right?
I can.
New recruits for this one.
So I've been away from Canada for not long, so I was just away for a year and a half. But still, it made me realize that we really had a unique environment in Montreal, at least when I left. The way that the research was conducted was very much organic, I felt. And that was was due to how much people would talk to each other from different fields. It was quite amazing that by the time I was at McGill, basically we had like interactions with Joshua's lab at University of Montreal, and that cross interaction really led to interesting ideas. And that's something I really miss, and I'm looking forward to see again. I think Joshua likes to say that research is a bit like taking a random walk with intuition. It's something that I believe as well. And I think we're really lucky that in Montreal and probably in Canada in general, we're allowed to do that sort of research, to just tinker about things, to just dream and come up with new ideas in a very creative manner. So we can't really do research having in mind some kind of business mindset. I don't think that's how research goes. And I think we have the right environment to conduct research back home.
If I can just add to that, I think sort of in reinforcement learning, we think about the horizon, gamma, right? So how short-term or long-term are you thinking about this problem? And I think the best research comes out of extreme long-term thinking. But that's also the hardest research to find support and funding for. Because returns for this, if you have gamma equals 0.99999, this might not come through for the next 10, 20 years. And at least historically, it kind of has had this track record of supporting researchers that work on things which don't actually right now work or aren't the leading regime. And if you listen to what I just said about my research agenda, these agents that learn to interact with others and account for humans in the environment and self-driving cars and theory of mind, that's not going to be in a product next year or the year after. So I think it's really maintaining this ability to explore a large number of diverse and potentially groundbreaking research directions, which Canada has been doing in the past and which I hope to be able to take part of in the future. And then there's the obvious answers around the fantastic talent and the collaborative nature of research in the Canadian ecosystem, which has brought me to Canada.
Csaba, any thoughts?
Yeah, like I'm just very thankful for Canada. I'm coming from Hungary originally, and I arrived to this country like 13 years ago, and I had the most amazing, pleasant experience. And I think my family right now thinks that we are Canadians. We try to fit in, and like we learn a lot. And yeah, like this culture is really amazing, very welcoming. And I think we should keep it like that, and that's very important. Everything else that was said, curiosity-driven research, collegiality, I think it applies probably across all Canada. I experienced personally that in Edmonton, but my colleagues are telling me that it's kind of like a characteristics of this nation, and like we have to cherish this, and it's really wonderful to have a country in the world which operates this way. It's truly amazing.
Nicolas, you're basically at Google Brain, down the hallway. You chose to also spend time in the academic context. Can you tell us a little bit why that's important to you?
I can. I need to choose my words carefully. I think industry provides a lot of tools, provides a lot of compute, provides a lot of very senior researchers. But for some reason, for the reason companies are built, there are very few people with free time in industry, mostly students. People who are eager to learn, and they want to try stuff, and they take the time to learn stuff. In an industry, you're evaluated regularly, and you might not care about it, but at the end of the day, you still feel like you have to produce. And I think Mila offers an environment where you have many students who don't operate on the same time scale. So most of the senior researchers in this room operate on a longer time scale because they've achieved what they wanted to achieve, and now they can think. But junior researcher in the industry, I think, operate on a much shorter time scale. But students still operate on the 3, 4, 5 year, the length of their PhD. And so being at Mila allows me to be surrounded by these people who still take the time to think about what they want to achieve several years from now, which is not as easy in the industry. Also, everyone's always very busy in the industry. Like you come to someone and say, can we talk? They say maybe next Thursday, which is something that doesn't happen at Mila.
And Sheila and Yaoliang, maybe you want to tell us a little bit about how you see the evolution in the Canadian AI ecosystem during the time that you've been here.
So I can start. So I guess when AI has changed, I've been in an academic position in Canada, I guess, since 2004, so a long time, and I've certainly seen things change a lot during that time, both in terms of the types of questions that people are addressing, and also in terms of the population of people who are doing that type of work. One thing I wanted to say, though, is that I think that the pan-Canadian AI strategy has been a very interesting model for funding. I've been in Canada for a long time, and of course I've seen the Canadian government fund a lot of industry to come and set up shop in Canada. They'll give incentives to industry to come and set up an office. But what's so brilliant about this program is that the money went to the researchers. The money went to do fundamental research. And as a consequence, all these industries came. And if I think about what's changed a lot in the last 5 years at least, with actually I think as a consequence of the pan-Canadian AI strategy, has been this influx of interest and companies coming to Canada to participate in this activity because of the hype and the sense that there's a lot going on here and that we have the best students and the best research going on in the world. So I think that's been something that's really exciting. Thank you.
Yeah, I agree with everything you just said. So I originally did my studies in University of Alberta, and then I went away for a little while and then came back to Bulletin. What amazed me a lot is the continuing investment of the Canadian government, of the Canadian business on the general area of artificial intelligence. We have a number of amazing people working in this area, probably the most dominant in the world. And we have a large number of students who are studying at different universities and the 3 institutes we have. Yeah, I'm super excited about the stage we are at now, and I think we all need to thank CIFAR for making this happening.
That's great, thank you. So let's talk a little bit about research. Reinforcement learning is a very hot field, lots of publications, lots of interesting things going on. It would be nice to hear from each of you about one specific piece of work that is, let's say, from the last 5 years. Not necessarily very, very recent, but can be very recent. Can be from you, can be from somebody else that you really like and would like to share with us. And we can start with Pierre-Luc and just come this way.
So I think over the last months or a couple of years, I think there's been quite a lot of interest in reinforcement learning to bring more methods from the control theory side. And I think I'm very excited about this too. One reason is I've always been curious about continuous time formulations, and I think it's a very natural framework to talk about this. In parallel to this, there's also been a lot of interest in now the neural ODE. So all these things kind of fit really well together, and it has strong roots into control theory. So I think in reinforcement learning, we can learn a lot from these methods, but of course there are still challenges that need to be addressed in control theory, and I think we have some expertise in reinforcement learning. We can make a difference for that. So in particular, when it comes to the problem of system identification and finding in learning models which probably we're going to parameterize with deep nets, I think we can do we can have quite of an impact. So I'm pretty excited about learning about these things these days, and I'm generally going to be looking forward to apply more of this over the next couple of years. And the second thing, which I've been quite excited about, I've mentioned it, is that body of work on hierarchical optimization, which has been there for a long time. So I think hierarchical optimization, in particular bi-level optimization, gives us really strong foundations to talk about meta-learning and reinforcement learning in particular. And we have lots of experts actually around that we can find. So I'm thinking at University of Montreal, we have experts. I'm thinking of Emma Fredinger, for example, who've been applying these techniques for a while to predict patterns in transportation networks for a long time, for example. It's just that they don't call it inverse reinforcement learning, but that's essentially what they do. So I think there's a lot of tools that we can learn from other fields and bring this back into our field and come up with better and stronger methods.
So I'm going to follow that same kind of pattern of thought. I think the division between the different fields we have, so thinking about optimal control, search, planning, and learning, and reinforcement as being different fields, I think that's been a huge detriment to the progress across these different fields. So you just spoke about optimal control and reinforcement, breaking down that boundary. I think what we've observed in the last couple of years or so is that the barrier between search and learning has been coming down, and I think that's a great thing. I think we have to start thinking about methods that combine all of these ideas to tackle how we can make decisions in a sequential manner. And in particular, in this line of work, I think Mu0, the recent result from DeepMind that showed how we can do implicit planning inside the learning context combined with search is a very promising direction. Because I think if we really want to have systems that can learn to generalize to new settings, we can't just pre-compute every single answer to every possible problem we might ever have. We have to be able to think on the fly and plan on the spot in order to generalize to new situations. And I believe this is sort of a trend that we'll continue observing in the next few years, really thinking holistically about decision making rather than thinking about this is what I do, this is what you do. And I think that's really good being at a conference like NeurIPS, where there are representatives from all these different subfields, and hopefully there will be these dialogues that can start off the new collaborations in these directions. In particular, for the future, I'm excited to bring those same ideas to multi-agent learning. Because when we're interacting in groups of agents, we naturally have to think about the points of views of other agents in the environment, and that's very compatible with a model-based approach.
Thank you.
It's kind of hard to follow up after these insightful answers. I think mine's going to be much more naive. So one is to basically follow up the interaction between, again, optimization and reinforcement learning. The reinforcement learning community used to be very isolated. I remember these workshops with 10 people in a room 15 years ago, and the same 10 every single time. And I think they've really opened up. And now there's a whole bunch of people trying to understand RL from an optimization perspective, bringing what does it do, what is this loss function, how can we change it, what are the consequences? And I think there's really a lot of insights that have been gained from this cross-pollination between optimization and RL. The other one I think is exciting is the link between optimization and generalization. So there was a question at the first panel. Optimization people used to think about there's a loss function I want to minimize and I don't care about the rest. And it's up to you to design a regularizer such that if I minimize this, it's going to generalize well. And we realized there are many, many more links between the two. And so understand this mechanism. There's a lot of work that came out of TTI, but also other groups about how can optimization affect generalization and what do you want, what do you look for. And I think that's really interesting, especially, again, coming back to RL, the concept of generalization in RL. Everyone talks about it, no one does it, no one understands what it means. And that's my understanding. And so I think there's really something to be done here to understand where generalization comes from, what it means, and how can we, when we train our models, we can affect generalization.
Sheila?
So I would echo a lot of the things that Jakob said, actually. I think one of the things that really excites me is this convergence of representation and search and learning all together. And I think one great example of that is indeed Mu0. The other thing and I think that's going to be a way forward. Related to that, I guess on the representation front, the other thing that I think is really exciting is the prevalence of language in reinforcement learning now. We see that with Jakob Andreas's work and with some of the other more recent works where language, human language, provides this wonderful abstraction for how we think about the world, a very purposeful abstraction. We use language to communicate with each other, to think about the world. We use it to communicate with computer programs, or with computers, and we also use it even just to think about mathematics. That's just another language, another abstraction we use to make sense of the world. And I think we're seeing more and more in reinforcement learning the use of natural languages or programming languages as useful abstractions for conveying rewards, for understanding causal models or representations. And I think that's going to be a very profitable area of research going forward.
Yeah, as for me, I'm really intrigued by the recent development in generative models, or more broadly, the density estimation problem. So I just came back from a defense last week, and when I talked to my statistician friends, they were puzzled, like, why are you working on density estimation? This has been studied like for so many years in stats. It's all very well known. But then if you start to think about what we do in density estimation, you spend lots of time and effort estimating a density function, and then when it comes down to the inference stage, you want to, say, marginalize the density, or you want to do some conditioning on the density function, suddenly it becomes really challenging again. And in certain applications, we want to have to learn a density function that you can easily draw samples from. This is where the new generative models are very powerful at. But then if you want to have a method that can, both easy to, you want to have a method that can be, you can do the inference easily and you can also draw samples easily, then suddenly, to my knowledge, there's not many methods that can give you that. And the other interesting thing I observed in this field is we are so obsessed with density functions. When we ask anyone about a probability function, a distribution, the first thing they come in mind is the density function. But there are many different ways that can uniquely characterize the distribution. And in fact, in the 70s, where Emil Pazen has done some work on, he has been advocating on using quantile functions, for instance, to do statistical modeling. And I think many of these recent generative models are exactly doing that. Like, how do we learn a quantile function, but in a multivariate setting? So this is what interests me or not.
Thank you. Csaba?
All right. It's interesting to have, I guess I have some perspective of what was going on in reinforcement learning, and talking about the days when there were 10 people in the room and maybe I was one of them. And maybe Doina was another one of them. And it were lovely days, but it's really good to have all of you here, and it makes the field more exciting to work in and to have these different perspectives coming in. And so one of the things that I'm really excited about in connection to this is this optimization viewpoint on reinforcement learning. Reinforcement learning, you can formulate it as an optimization problem. It's that, like, that's the definition of it. It's a weird optimization problem, though, right? You want to maximize the return at every state if you are in this MDP world, which is like a multi-criterion optimization. And if you try to merge this with generalization, suddenly you see that, like, you can't do this anymore, so you have to somehow sacrifice your original objective. And now maybe you change your objective, and you find that even the new objective is difficult to optimize. So there are really interesting questions around how can we efficiently optimize objectives or the objective that you choose at the end, because these problems just have too many variables, and like if you write it as a constraint optimization problem, too many constraints. So the question is, what are you going to do about this? Well, the standard answer from CS is that you have to solve some relaxed problem, and then you can try to look for tools for doing that. But until quite recently, not many people care that much about this perspective. I mean, like, during the many years, time to time, there were some isolated attempts to use this approach, but there was no, like, significant effort, like a bigger community caring about this problem. So I feel that, like, these times are really exciting because we have this influx of great new minds who are excited about our field, and I expect to see many wonderful new results. I could quote a bunch of papers that I'm excited about in connection to this. Like, people are discovering these days that, for example, if you somehow like make assumptions about different assumptions, people do make different assumptions in reinforcement learning of what can you represent easily, like additive value functions or policies or occupancy measures, or maybe the model. And people find big differences in terms of what these assumptions mean, and that's like really interesting place for a theorist to be, because you want to, categorize and understand how these assumptions relate to each other. So I'm really excited about this.
Excellent, thank you. So reinforcement learning is very prominent, partly because it's now able to solve larger problems. And I think a lot of us are also excited about potential applications. But a lot of the stuff that you see currently as applications of reinforcement learning are games. And then in terms of value function estimation and learning algorithms, there has been some success in neuroscience in terms of modeling. And so one of the things that I'm curious about, I'd like to hear from the panel, is either what is the application area that you would be most excited about, that you think would be really good for reinforcement learning to be in and make an impact, or what is a problem in reinforcement learning that we really need to solve in order for it to become impactful in practice. And I will go in random order for this one. And whoever speaks can't say what somebody else said already. So I want to get 6 different things here. So anybody like to start?
I can. So I'll answer the second question because I have no clue about the first one. To me, there are 2 things that we could be much better at. The first one, again, it's a personal bias. It's reusing past trajectories. So some people have collected trajectories using maybe different policies, or even in slightly different environments, since we're talking about generalization. How do we use these? And we tend to be extremely bad. And off policy is really the stuff we do when we have no other choice. But I think there's so much to be learned from these trajectories. And so it comes back to what I was saying at the very beginning, which is we extract, I think, very little information from our experience, and we should be able to extract much, much more. The other aspects I think that we could do, and I made everyone at my table suffer with pictures of my kid. I just had a kid. And this idea that you don't need a reward to learn about the world. And I think right now, reinforcement learning is not very good at this, at understanding and creating a representation of the world without having a specific objective in mind. So we can, put in some inductive bias and say that's what the representation should be, but just exploring the world, what is a proper exploration mechanism? I think it would be great to have something along these lines.
So off-policy learning and no-reward learning, to summarize? Okay, cool.
I will just add to that a little bit. So I think there is a sort of like a meta point here to be made. So what is the reward that incentivizes researchers in machine learning? And that's commonly being able to demonstrate that your method accomplishes something amazing that wasn't done before. Commonly, this is done through benchmark environments or state-of-the-art. And I think this has been driving sort of the focus of reinforcement learning in games. So I think what we're missing systematically are benchmark environments that are still tractable, we can make progress now, but that are closer to the kind of problems we hope to address in the real world. Right? So for example, I study this question of theory of mind, and I currently address this in a card game, Hanabi. This isn't because I think the card game is super practically relevant, but it's because I can study how agents can learn to interpret the actions of others and reason over intent and partial observability in this card game setting. What we don't have is a simulator that does the high-level components of self-driving, which have these same challenges, but lets us address them and tackle these questions in a way that don't have to go and interact with the real world right now. Because the questions that are limiting progress of reinforcement learning, sample complexity, robustness, reliability, those just aren't as relevant in the games benchmarks that we use currently. So I think as a field, it's really important to think about what are those big application areas that we want to see progress in 5, 10 years, and what are the simulation environments that we can develop as benchmarks today that will actually encourage research in these critical directions. So I guess instead of answering the question, I'm posing 3 more questions with my answer.
But the upshot of it is benchmarks.
It's benchmarks which are targeted towards real-world problems,
Okay.
rather than benchmarks for the sake of showing superhuman performance in a game. Let's show good performance in a relevant task rather than superhuman performance in a potentially less relevant task.
Okay, cool. Sheila?
I guess there are lots of different interesting challenge problems, but one that I'd like to focus on, I guess, is taskability. So I think that we incent reinforcement learning systems by defining reward functions, which are mappings from states or states and actions in states to some sort of a number. But if you think about a lot of the classical work on AI planning or in robotics, we want to be able to tell our agent what we want it to be able to do, and it should be able to figure out how to do it with, not necessarily by learning from scratch all over again. And so I think taskability is a really important problem, and I think it's one that's been addressed by the classical or the GoFi planning community. But what's interesting that the GoFi planning community does not know how to do is how to do the low-level control issue. So for example, I can plan, I'm sure all of us could imagine writing a program to plan to get from where we are today to our hotel room, for example. But to understand how to move your joints to get off of this chair or to pick up a cup, those are things that reinforcement learning is very, very good at, those low-level skills that require some sort of adaptive experience over time. And so I think some sort of combination of the two is a fruitful place to look for research in the near future.
Okay, thank you. So high-level and low-level interplay of,
so I'd say
planning and narrow.
Yeah, and taskability.
And taskability, perfect.
And generalization. Taskability and generalization, I think, are...
So I think I'm going to answer your question more on the practical side. This is something more that I would like to work on over the next years. I think there's a lot of potential for applying reinforcement learning methods and control methods for computational sustainability and climate change questions. So it's not something I have expertise in these topics, but I'm hoping at least to find collaborators to work on these questions a bit more closely. One reason is I think that all of us are aware that climate change is something we need to tackle quite soon. But from a research point of view, I think these problems also are very interesting because of their structure. Oftentimes, when we think about natural system, it involves some kind of dynamical systems. When you talk about dynamical systems, you might also think about ODEs and continuous time formulations, which are things that I find interesting these days. So this is something that I'm looking forward to work more on. But once again, there's a need for collaboration to do these things, to find these interesting problems. But being in Canada, I don't think it's going to be that difficult to find these problems because of our natural resources. I think there are many problems such as optimal management of fisheries, for example, is a classic one, which we can do sequential decision making. There are also lots of potentially very impactful application for better control system for things, boring things like HVAC. So all things, air and temperature control in buildings, these things can be automated, can make a big difference if we can have a better control over the energy usage. So these are all applications that I'm excited about, and I think that could have a huge impact in the next 5 years or so.
Wonderful, thank you.
Can I?
Go
Yeah,
ahead.
so I've been trying to think hard about the reinforcement learning I've learned from this man here. So one thing I do remember is, and I agree with Nicolas on the off-policy, importance of off-policy learning. So one thing I remember is one of the first few sound off-policy learning algorithms that have been developed in the AI lab at University of Alberta is that they're so complicated. You have to employ 2 time scales, and if you look at the proof, it's extremely, extremely complicated, mostly by this man here. And the techniques, if you look at the techniques they use ODEs. But one thing I think it would be great if we can largely simplify the analysis of this algorithm. And I think there's a great hope here because the ODE approach has been very popular in the machine learning community. For instance, we have the ODE approach for neural density estimation. We have people have used ODE to analyze some deep architectures, right? So I think there's a lot of promising questions in how do we simplify off-policy learning algorithms.
Thank you. Csaba?
Can't disagree. Sorry, too loud. Yeah, I'm not sure how complicated that analysis is, though, but
We can
in my
try
view,
to get a
it's pretty
blackboard here.
yeah, like it would be nice. But it's true that there is a lot left to be done in off-policy learning. Just to mention, like even for Bennett's, like I like to study the simplest setting in which you already find some gap in your knowledge, and that often leads to Bennett's, and it's ridiculous, but that's the truth. And so already in Bennett's, if you have a batch of data, then we don't know what is a minimax optimal algorithm to estimate, like, okay, it's like a little bit more complicated than just minimax optimal. Minimax optimal we know, but like near instance optimal algorithms, we usually do have that, and then that means that we do understand how to adapt to the particular instance that you're learning on. And just the fact that already in Bennett's we don't have this kind of shows that it's we need more people looking at these problems. So off-policy learning, definitely agree. At the risk of repeating myself, I mean, designing algorithms that scale, computationally efficient, sample efficient, and can deal with large state action spaces. We have those in very few corner cases. And I think that like these are important because you're going to build on the top of these, right? So there are so many other issues that you also want to address. We heard about very long time scales, so maybe that brings up temporal abstraction, because maybe functional approximation can be viewed as doing spatial abstraction, but maybe you want to do action and temporal abstraction. But if you don't have foundations to build on, so all those algorithms that people try to use are, just like shaky foundations, it's not going to fly. So sometimes we need to go back to these simpler problem settings and then find those gaps and work on those gaps. And exploration was mentioned in connection to having no reward, but I don't know, like I'm going back and forth between these two views. Even if you do have the reward and you rarely see the reward and you're kind of like already solving a no reward problem where the reward is so rarely seen. So if you want to claim that you made progress on optimizing some reward while learning online in some big environment, then like you're already addressing the problem of learning in the face of no reward, because maybe the environment is such that you will only see the reward after a long, long period of time, and what are you going to do in the meanwhile? But nevertheless, this problem is, well, it has been occupying me for a decade or so, but again in a simpler setting, because, you know, like, these complicated things are just too complex. So start with something simple and then grow from there. But yeah, like exploration is something that together with functional approximation and the scalable algorithms, it remains a big open problem and a huge challenge for the field.
Thank you very much. So now we have our list of open problems for reinforcement learning, courtesy of our new CCI chairs. Now in 5 years we get back together and it'll all be solved, maybe, or at least we'd have made good progress. I would like to open the floor up for questions. There's a couple of mics in the back of the room, if people would have any questions. Or I suppose you can also shout it out.
Better to use the mic for the webcast.
Better to use the mic. Okay.
Hello, my name is David, and I just wanted, because one of you mentioned the relevance of having suitable environment to test our models with respect to the applications within which we're going to apply them. And I was thinking, yes, in the world, sometimes we're supposed to work in continuous time, so having continuous time models would be appropriate, and also the right environment to evaluate them. But I was thinking, I also thought about the fact that recently, I don't remember that anyone has been focusing on real-time interactions. Mostly within the framework of RL, we assume that we can stop the environment and send commands to it, whilst in the real time, we won't have to deploy their model. The problem, in fact, would not be, you might have problems in which you have asynchrony between your environment and your model. I encountered that during an internship, and it sort of made me, I wonder, do you think that this would be interesting to explore in the future, context in which you have asynchrony between your environment and your agent?
So I guess I mentioned the benchmarks and the environments, and I think what you're saying is a great example, right? So as a researcher, as long as we stay within these game environments, we have full control of the step function, we can call it whenever we're ready. We may never have thought about the fact that the real world progresses even while I'm sitting here thinking about my answer to your question, right? And it's exactly this kind of problem which I think requires us to start thinking more about not what we're going to solve in the next year, but where reinforcement learning could actually be useful in 5 years' time, 10 years' time, and start talking to application areas, and then start developing benchmarks environments that do include this question of synchronicity, where the information comes in in a continuous time, where actions can be taken in a continuous time, right? So I think these are exactly the questions that are relevant, and I can't think of standard benchmark environments in reinforcement learning right now that are even near those kind of problems.
Yes. So if I can just add a little bit on this. I think there are benchmarks, not exactly in our community, but I think the gold standard for this is robotics. And we have our colleagues around who work on robotics, and these are inherently a synchronous system. When they send a command to the robot arm keeps on moving at different time scale. Everything is like natural time scale. And I think they have to deal with these questions. So I think we have a lot of things that we can learn also from these communities in robotics and control. Where real time is oftentimes something that is inherently like the important. Yeah.
Okay, thank you.
Okay. Chris?
Okay, so I hope this is not too pointed of a question because I want an answer for myself as well. But I guess this is for Csaba and Jakob in particular. So when we think about picking either models that are simple on which we can have some sort of theoretical grasp, or when we pick benchmarks where we can actually start working and evaluating things, how do we avoid the trap of picking ones that we already can solve and that might not generalize to the more interesting settings that we actually cared about. You know, everyone who tries to prove things knows that often you start with a smaller set of assumptions and you go until you hit a wall, and then you put the wall into your assumptions. And similarly with benchmarks, we can often sort of overfit to that specific thing without realizing that we weren't actually generalizing to the full problem we cared about.
I do have a short answer. Just be honest as a scientist and be very clear about the limitations of what you're doing, and always keep these in mind. And that's it. I don't think it's very complicated.
I have a slightly longer answer. Obviously, I stand by being honest. I think that's always really important. But I like to do work which encompasses both a simple toy example. We can show that a method works in principle and can be easily understood and reproduced, and then also show that it scales to a large benchmark problem. And the comment I was trying to make about the issue I find with our current benchmark problems is, which I don't see them as a stepping stone towards real-world problems. And I'm actually okay if you overfit on a problem as long as that problem is something that we care about as humanity in the real world. If you get really good at solving climate change, I'm okay if you can't also tie my shoelaces, right? As long as you solve climate change for me, that's fine. So I think the issue of sort of like overfitting and reinforcement learning is just that we happen to optimize on objectives that we don't actually commonly care about. So it's time for us to start thinking more about how we can align the kind of tasks that we're solving in simulation to test our methods with the kind of problems that we actually care about as society, as humans. And then, obviously, within that, there'll be questions like, oh, we have to truly generalize, right? What does that mean? You can never interact with the same environment twice. Every time you go and call reset, it's going to be a slightly different world you interact in. It's going to be asynchronous. It's going to have a lot of other interacting agents and all the other issues that the real world has, which don't currently reflect within our benchmarking environments. But I think there's a lot of open questions around what those benchmarks are and how we can actually evaluate our methods truly and accurately in them. Always keeping in mind that we need to be honest when we do so.
Okay, and we have time for one last question.
I'll try to make this count. So in reinforcement learning, we sort of have an understanding of, for example, MDPs, right? That's a formalization of reinforcement learning. But a lot of these problems that we're talking about, like exploration or no reward learning or generalization, we don't really have a formalism for what we are trying to do. And as a result, when I see different people talk about exploration, they're talking about different things, right? And I don't understand how we are going to formalize these problems, because we have an intuition of what they mean, but we don't quite have a mathematical formalism of what we're trying to accomplish. So where do you see formalization along the path of solving these problems? Like, don't we need to figure out what the problems are first, precisely?
Not sure whether, well, by the way, Roshan is my student, so we could have this private discussion as well. I think we had discussions about this, but I think that I would push back a little bit of saying that we don't have the formalisms. I think we do have the formalisms. Maybe they're a little bit buried in the theory papers that people don't necessarily that often read. And maybe the theory papers are to be blamed because maybe they're not as accessible as they should be. But I think that it's more like that we have many formalisms for studying all of these questions. And there are no, unique choice or choice that would have been selected by the community as the real one. So maybe this goes back to the previous questions, previous panel of do we have grand challenges? And because of that, from a little bit of an outsider perspective, it may look like that, everyone's pulling in different directions. But I hope that that's not the case, and we read each other's papers and we try to understand what people are saying. I think it's truly very important that we are clear about the problems that we are trying to solve. So always start with the problem definition. This is the first thing that I try to teach for all my students, right? And then it should be better. This is just gives you more clarity and gives the ability to compare different works and to recognize whether you're making progress or not.
If I can add just one thing, I think the clear definition and formalism may be easier to come up with these definitions once you have an actual problem in front of you. And I'm saying this because I've realized as a researcher that I haven't been working really much with concrete problems beyond, video games and things like that. And I think moving forward, I want to try to think a bit more about concrete problems, the way that my colleagues in engineering departments would do. And I think perhaps if we were to do so a little bit more, the clear formulation for the thing we're trying to do would be clearer as well. So I guess my answer is if maybe we need to wrap and put a bit of context around the things we're doing in general.
Well, thank you very much for your comments, and I really look forward to lots more exciting reinforcement learning research in Canada in the next years. Thank you.